Programmable Logic Controller class. Our goal is to systematically cover all of the bases. I'm going to discuss a lot of the things that you wouldn't consider when you were preparing to teach a programmable logic controller class. There are hundreds, if not thousands, of individuals out there who work well with PLCs, are in a position where they could train people. They're in plants, factories, engineering companies, service companies, and they have the knowledge of the PLCs, but not necessarily the resources or the teaching skills. Now, we can't do everything in this little presentation, but I will warn you up front, it's not going to be a 5-minute presentation. I'm going to cover everything in as much depth as I can, and if it's going too slow, feel free to use the fast forward. So I'm going to start right at the basics. That's reading, writing, and arithmetic. Some of you are probably laughing right now. However, you would be surprised. And by the way, I have thousands of hours in the classroom, live classroom, in front of students teaching these subjects. You cannot determine who's going to be in your class. Or there'll be people in your class that don't want to be there, but they're forced to be there in order to maintain their job status. But you will come across people who are challenged when it comes to reading, writing, and arithmetic. Now, it's hard to imagine anybody that can read and not write. So reading and writing, I kind of group that together. And arithmetic is extremely important in all phases of life. It allows you to logically conclude what's fair. When you work with an equation, this and this or that plus this equals this, being able to model the situation in your head, and I mean with control systems too, to come up with equality is an arithmetical function. So that's obvious, reading, writing, arithmetic. The one that's not so obvious, but you're going to understand it immediately, is visual spatial reasoning. Right away you probably have an idea of what that is, but let me make sure that you understand. This is a category of reasoning skills that refers to the capacity to think about objects in 3 dimensions and draw conclusions about these objects with limited information. Someone with good spatial abilities might also be good at thinking about how an object will look when rotated. Myself, I can visualize almost anything that I've seen and have good information on in 3 dimensions and rotate it a full 2 pi steradians. That means I can look at it from any angle. Visual spatial skills are of great importance for success in solving many tasks in everyday life. If you can't visualize in 3D, you're not going to do well with PLC programming and troubleshooting. They also have something they refer to as spatial intelligence. That's the ability to comprehend 3-dimensional images and shapes. Now, you're not going to teach visual spatial reasoning, but you need to be aware of the individual levels of the learners in your group that you're teaching. Without a reasonable level of skill in this area, the learner will struggle to understand the relationship between a controller and the process that is controlling. Skilled trades, meaning hands-on people, that could be engineers that spend most of their time out on the shop floor, technicians, electricians, they have an edge over everyone else when it comes to this type of learning, to learning a relationship between a virtual process in the computer and the real process that is controlling. One exercise that you might consider is having everyone in the class build something that requires measurement, cutting to length, and assembly. Requiring some movement within this something, such as things that slide or rotate, would be a great improvement on that. One simple way to do that is to have them build something like this. Now, these things are cheap. I think this one's $40 on Amazon. And there's parts that have to be glued, and there's parts that you don't dare glue, that actually have wax applied as a lubricant. So you could make this an assignment. In other words, you can make it part of the course. And if you're charging for the course, or they're paying an application fee, then that would include this $40 kit. And at the end of them assembling it, you'll see the people that have good spatial reasoning and those that don't. Now, what can you do about it? Nothing more than be aware of their spatial reasoning when you're doing word pictures. The best explanations are always word pictures. And they usually begin with, picture this, and then you go on with your word picture. Here's a couple more of those kits. All of these are within the $50 range, and they're from one particular manufacturer. They're ROKR. Notice that they all have hand cranks. Another project that you could give the learners is to build a electric motor drive, which means they would have to build the coupling. You see where the handle attaches to the shaft that drives it? They would have to remove the handle, the crank, and then develop a coupling that would fit to a small DC motor that you run on batteries. These are just things to improve their spatial reasoning while they're going through the initial part of the course where you're doing a lot of talking. Now, if you got a 5-day class, you don't have time to do this. Okay, visual spatial reasoning. Again, there's nothing you can do about reading, writing, arithmetic, and visual spatial reasoning other than when you go into the classroom, you need to be acutely aware of where they are all at. Doesn't mean you ask them a bunch of questions, but you need to be looking to see who's challenged. And another category would be physics. Now, when I say physics, I'm going to say electricity, mechanics, and the physical laws. You don't have to know these things, and you don't have to have visual spatial reasoning, and you don't even have to be good at math in order to take a PLC course. But to be successful at the goal of the course, you will have to have a reasonable level of skill in all of these areas. Fluid mechanics, pneumatic systems, hydraulic systems, and these are just a few examples of understanding fluid mechanics. The one in the upper right-hand corner, that's a shock absorber. And if you understand how a shock absorber works, and remember, fluids are gases and liquids. So whether it's a gas or a liquid, it's a fluid. So understanding how a shock absorber works with the check valve and the size of the ports that allow the fluids to compress and transfer from the upper to the lower chamber back and forth. There's an extend and a retract rate that shock absorbers have. That's understanding fluid mechanics. And then we have a basic hydraulic system, and we have an actuator, a cylinder. We have a directional control valve, and then we have a power pack, which is comprised of an electrically driven pump and a tank, a reservoir. And the important thing for them to understand is the relatively incompressible nature of liquids as opposed to gas, and the control valves that route the pressure from the pump or the motor or the air compressor to the actuators. But they need some sort of general idea of fluid mechanics. Then there's also torque. We just take torque for granted. Electric motors is the best example of torque. And then, of course, electricity is really the big one. Of the three, electricity is the most important because that's what industrial control systems are. They run off of electricity. So they need to understand AC and DC. When it comes to the measurements, is that it gives you an inherent understanding of the relationship between volts, amps, and resistance. Now, watts we put in a separate category because watts is a combination of volts and amps. Its voltage is the pressure, and amps is the movement against the R or the ohms. They need to understand Ohm's law and, of course, series and parallel circuits. If they're short on any of this, they're going to struggle in class. When you get students or learners, and then, of course, computer skills is absolutely paramount. They at least have to be able to turn the computer on and off, open programs, close programs, open files, save files, close files, and manipulate their way around through the basic operating system of the computer. In this case, it would be Windows. So they need to understand the relationship between Windows as an operating system and the boundary to where the application starts. So all Windows applications have a similar look. Those similarities are the Windows operating system. Everything else is the actual application that you're using, the commonality of the Windows menu systems, etc., to do whatever it is that you want to do with your computer. And then, of course, and this, I have a dividing line here, because this is where you're really getting into PLCs, and that's understanding industrial relay control circuits and symbols, because this is where it all started. And 90% of all the programs out there installed in machines running, and I don't care whether you're a electrician, technician, or engineer right out of school, and you go to work for a company. Now, if you go to work for a systems house, then you might be writing all brand new programs for all brand new machines. But 90% of the people that are going to work with PLCs are going to be working with the installed base, which means ladder logic diagrams, relay logic. And to properly teach ladder logic diagrams, they have to understand these symbols. You've got all these learners that you're trying to get to one location on the map. All of these categories are things that you're going to have to be aware of and guide your people through to get them to that big red dot. You're going to have some people, it'd be nice if this is all that you had, were people that had some relay circuit knowledge, and you were going to move them into processes or understanding processes and their connection with the PLC control, the software, the memory, basically using a PLC to control a process. This would be the ideal student, that they already understand relay circuits and might have a little knowledge on processes, and you're going to give them more. However, you're also going to get people that are coming from way out in left field that don't have any of these things. Minimum spatial reasoning. Maybe they got some math, but not physics. Maybe they got some computer skills, maybe they don't. But no relay circuits and no real experience with processes. These days, because of all the STEM programs, I think we're going to see more people that aren't as far out in left field. But there's a big difference between sitting at your desk at home with an Arduino and a breadboard and actually going out onto a shop floor and working with processes that are in motion and cannot be interrupted while you figure out what's going on. And then, of course, you're going to get some people that are starting at other places in the process. So all of these people have to know where they're starting from to know how to get to the destination. Now, if they don't accept where they're at, that's another problem for you to deal with. They think they already know it all, and you can see they don't, then you're going to have to figure out some way to kindly move them to a point where they understand where they're at. Because if you're going to go from, that's someplace in Texas, you're going to leave to Texas, go to St. Louis. And if you don't know where you're at, and you're actually in Montana, and you head off in a direction towards St. Louis from Texas, but you're in Montana, you're not going to end up hitting St. Louis. So you've got to know where you're at to know how to get to where you want to get to. And of course, just some more examples. Now here's one that you're in Phoenix, Arizona, and guess what? They're going to hit the edge. Maybe you'll catch those people, and then you can kind of pull them in to the gravity of the subject in the center there. You got to get them to understand what they don't know. Most people, they just don't want to admit what they don't know. And we're all like that to some degree. Nobody likes to look like an idiot. However, they learn faster and better if they just accept where they're at, and they're going to get to the destination quicker. So you have to know where your students are starting from to know how to get them to the destination. And you're going to do that during the very first session when you're going through all of the housekeeping and everything, where the bathrooms are, what time class starts, what breaks are. As you're talking to them and you start getting into some technical subjects, you got to be able to read their faces, their fidgeting, and their what gamblers call a tell. And that's a little thing that they do when they're nervous or they don't understand what you're saying. Because some people are too proud to raise their hand and say, I'm sorry, I'm lost. What did you mean by that? These are all personal skills, interpersonal skills, people skills. And as an instructor, you don't automatically have those. So you may have to develop those, or you may have to prepare your class in a way that does not highlight your weaknesses in that area. But there's so many thousands of approaches to this that I can't cover all the possibilities. And actually, the only one that I have the real experience with is where I'm at and what my people's skills are. Now, I have thousands of hours in the classroom. I've already been through my baptism of fire. Matter of fact, the very first class I taught was on solar energy, and there were 237 people in the class. It was in a high school auditorium, and it was 2 nights a week for 6 weeks. Fortunately, I was well prepared, and I'm a typical geek that I do a mind dump on people. I'll tell you everything I know whether you want to hear it or not. There's an advantage to doing that, and that is that it's pretty easy to cover everything and ignore that people are sitting there, ready to shoot themselves, and their eyes are flickering because you're saying way too much. Beginning with electricity, computer skills, and some industrial relay control circuits and symbols. Again, the computer skills is too late now once you got them in the classroom. And you're not going to do much with their electricity, but you are going to enhance their knowledge of industrial relay control circuits and symbols, because that's part of teaching PLCs, is explaining the origin and the reasons for ladder logic diagrams. So you're going to start out with some lectures, and you're going to start out explaining industrial control. You're going to start explaining relays. Then at some point you'll make a transition from relays, coils and contacts, to memory, bits and instructions, and that relationship with ladder logic diagram. A good course has to have hands-on experiential learning. And the primary element of hands-on experiential learning is what they're using for a learning station. Now, if they're using the laptop with the simulator, that's not an impossible situation, but that's very ineffective. The reason a lot of people use that is because it's either free or it's very inexpensive. You don't have any PLC hardware to deal with, cables to deal with, power cords, extension cords. Everybody, or in groups of 2 or 3, has a laptop, and they just kind of take turns working with a simulator. The problem with simulators is they don't necessarily stay up to date. When it comes to the basics, there is no up to date because the basics stay the basics. But it's not the same thing as writing a PLC program, downloading it into the PLC, and then exercising some input devices and seeing the output devices respond the way that you thought they would. That cannot be replaced with a simulator. But if that's all you got to work with, then by all means use a simulator. Now, learning stations, and these aren't, I just grabbed these off the web. This is a nice looking little station. I like oak, but it is deficient in some areas. It's only got 4 inputs and 4 outputs. Now, if I look at that PLC closely, I see it looks like a PLC Direct. It looks like it has 8 inputs and 6 outputs. If you look at the LEDs on the top edge of it, unfortunately, they're only using 4 and 4. The disadvantage to that is that limits the practical applications that they can do. I'm sure whoever designed this and built it just said, well, yeah, but you don't need that. Well, the only reason I started building my own digital field device simulators is because I needed 6 inputs and 4 outputs for almost all the practical applications. In other words, you need a light for a motor or a solenoid. You need switches for sensors, but you can also have too many. So 6 inputs and 4 outputs is not a bad ratio. Currently, I have digital field device simulators that are 6 and 6, and there's a reason for that. But typically, I don't use all of the outputs, but I wire them all up just in case the learner wants to do that. Something else you'll notice here, that you don't see any connection to 115 volts AC. You see a power adapter. And the ways those are designed is it's pretty hard to get shocked. I recommend that all of your hardware trainers have no finger contact safe points. In other words, use 24 volt DC power adapters, not power supplies that have open exposed terminals connected to line voltage out of an outlet. Here's another one, another company. Now, this is really nice, and it has like an L24E Compact Logix controller, and it's a controller because it has I/O and the processor all in one piece of plastic. And just looking at that PLC, I see 16 inputs, 16 outputs. I see analog in and out, and I see high-speed counter, the pink. And then I also see a panel view. So this little trainer has everything, but these things are not inexpensive. I don't know how much this one is, but this is way above what you need just to teach a PLC class. Be nice to have, but you're going to be hard-pressed to convince your boss to buy a couple of these. Now, if you're only going to teach 2 people at a time, and you only need 1 of these, then it becomes more cost-effective. Here's another one. And this one has a Micrologix 1000 on it, which has RS-232, that 8-pin round DIN connector. However, my reservations about this type of design is that the student is going to be directly connecting conductors to those screw terminals on the PLC and all those other devices. If they booger up the screw on the PLC, then you've got a lot of work and expense on your hands. So typically, I extend wires from the terminals on the PLC to inexpensive terminal strips and let the learners booger those up. Also, one nice thing about this demo station, this learning station, is that it's got some industrial semi-NEMA type push buttons, a selector switch. It's got a little sono alert buzzer so you can make some noise. It's got a starter, a contactor, limit switches, and some ice cube relays. And that's nice. But to teach a PLC class, you don't need them to wire up directly to a motor starter, a contactor, limit switches. It's cool. okay? But it's added expense, and what prevents a lot of PLC classes from taking place is the expense. Now here's a couple made by another vendor. These are both nice. If I was going to teach a PLC class and they gave me these to use, I'd be happy. Industrial Concepts makes nice little trainers. So we got a Omron PLC, and then we've got a Allen Bradley Micro 800. And they are cost effective. In some cases, they don't have enough I/O, and they may not have the contact form that you want, meaning normally open, normally closed, momentary versus maintained. So I see on the one, two inputs 1 and 2. Those look like they're toggle switches, so they're maintained. And then N input 5, input 3 and 4 are momentary. Now, I don't know. The green might be normally open, the red normally closed. I don't know for sure. And then the other one has similar type of devices, but I also see it looks like a proc switch. They got a Son alert, output 8, that's a buzzer. And I'm not sure if output 6 and 7 are push buttons and inputs, not sure. I see input 8 is a push button that looks like it's got an LED behind it. But these are nice, and they're very cost effective. I would not hesitate to use these myself. Okay, what we supply to the instructors, schools, universities, and people that use our materials. And you have 3 images here. What we sell is on the far left. We just sell the stand, and that's made out of 80/20. You're more than welcome to copy that design and build your own. The only reason that we charge what we charge for these is because of the labor of ordering this stuff. You got to cut it. You got machining operations, tapping, drilling, and it's designed to hold almost anybody's PLC on that horizontal DIN rail. Then on the bottom, we have mounts for the digital and analog field device simulator. Now I only show the digital there with the 6 toggles and 6 LED lit push buttons. But I also threw on the DIN rail that goes with it, I just threw some terminals, relays, and stuff on there to show you what it might look like. So I have a Micrologix 1400 with a 24 volt DC power supply, a digital field device simulator, and some relays and contacts. Exact same stand. I show a newer Compact Logix with some point I/O, 24 volt DC power supply, and the same conglomeration of field device simulator and relays. Okay, this is a different stand, but it's adjustable. Also more expensive, and the parts are expensive. So if you go to 80/20 and start pricing this out, you won't think my price is so bad. But you don't need anything this fancy. I'll show you some simpler things. But these are nice for the classroom because they are vertical and they're portable. Now here I show the same configuration I showed in the last image, but I show an analog field device simulator also. Okay, these are the 2 field device simulators that we use in all of our programs. The digital field device simulator, and there's 6 inputs and 6 outputs. Now remember I said 6 in and 4 out is about nominal for doing basic practical applications, switches for sensors, lights for motors, maybe the blue LED light is for low raw material supply, etc. What separates this digital field device simulator from all the others is that each toggle switch is interconnected to the adjacent momentary Form C contact push button. Now, and the push button is also a red LED or green or orange or blue, but they're wired together so you have a 4-state input. Maintained on, right now it shows that it's maintained off right now. So in the position it's in right now, input 0. In the opposition, it is wired in series to push button right next to it. So you end up with 4 states. Maintained on, if you flip the switch up, and then if you push the button, it's connected to normally closed, and so it opens. If it's down and you push the button, it's connected to normally open, so it closes. So you have maintained on, maintained off, normally open, normally closed, because sometimes in a lab, if it's a photo eye and an object is passing, you want to simulate it sensing it and then not sensing it. So what happens in the lab, students are so concentrating, they'll hit the toggle switch to turn on, saying that the photo eye sees the part, and then they forgot to turn it off. Then they go on to the next phase to turn on the next photo eye, and then the logic doesn't work because they forgot to turn off the other photo eye that had already passed by. So this type of a digital field device simulator gives you the best of everything. The analog field device simulator is really simple. You've got 2 digital displays, and those 2 digital displays are connected directly to analog voltage outputs on the PLC. They aren't controlled by anything else. They're connected directly to analog outputs, 0 to 10 volts. The binding post underneath each display, that allows you to take that analog output and extend it to a VFD or some other device that you want to experiment with a analog voltage signal. That's why we call them field extendable. Now, directly below there, you see a green knob and a yellow knob. Those are potentiometers. And below the knobs, you see a switch that says potentiometer 0 to 10 volts DC. The position that it's in right now, that toggle switch, it is connecting the binding post below it, input 0, to that input on the analog I/O module. If you flip the switch up, then it connects the 0 to 10 volts from the potentiometer into the analog input. So this device does not supply any analog values other than input 0 and input 3 from those potentiometers. What you have here is you can flip the switches down and then connect your own analog values into those binding posts and have them go directly into the analog inputs on the card. Input 0 and 3 are only going to be 0 to 10, whether it's the pot or field extended. The two in the middle, input 1 and input 2, notice that they read 0 to 10 volts DC in the up position, 4 to 20 milliamps, the down position. That's because some analog cards allow you to connect up both, 0 to 10 or 4 to 20. They have voltage inputs and current inputs. So these are the two mainstays that we use in all of our trained equipment for field device simulators to the PLC. You can build these yourself, by all means. The only reason I build them is because it's what I want when I'm teaching class, and no one else would make these for me. Believe me, I contacted these other companies to see if they would build these for me, and they never even answered. So I just went and built my own. And this is a full-blown Micrologix 1400 learning station. Let me explain to you very quickly what's here. You see all those terminals along the top? Well, the yellow and brown ones, they allow you to connect that analog field device simulator into the analog inputs and outputs on that 1400. That allows you to use this just for digital only, or you can set the analog unit next to it, jumper the wires over, and now you have access to analog inputs and outputs to this 1400. And that 1400 is a BXBA. And by the way, the only 1400s that you want to use are BXBs or BXBAs. And that's because of the availability of PWM, PTO, and high-speed counters. The other connectors up on top there, orange, white, black, blue, black, green, black, and by the way, you also see some fused terminal blocks. That's in case you want to bring in external power instead of using the power adapters that we supply. But those two green terminals are two outputs that aren't wired up to the 6 lights. So 0 through 5 are those 6 LEDs. 6 and 7 go to those green terminals. Same thing on the input side. Those switches and push buttons are wired up to 0 through 5. Those two terminals are 6 and 7, which means that you can have external projects without the student pulling back the little flip lids and running wires and connecting them up to the controller, and then they don't have a common, black wire, the minus DC wire if you want to call it, or the plus for outputs or whatever. So these allow you to be very creative with your lab projects that you develop. And again, these are easy to copy. There's no rocket science here. Light switches, a PLC, and some terminals. The 3 white are connected to output side. So they would be, PWM, pulse width modulation, pulse train output that you would use for steppers or whatever. And then the orange ones go to the inputs, and they are specifically for a high-speed counter. In some cases, the white terminals are connected up to the same terminals are connected up to outputs on the digital field device simulator, which is fine. And same thing with inputs. If there's a duplication, you just leave all those switches in the opposition and you use the white, whatever's hooked to the white terminals and the orange terminals in your project. And again, you can build these yourself. There's no rocket science here. These are what we use in classroom. And you can see some strong similarities there. And in the case of the analog card that you see on the L32E or Compact Logix, that analog, that device right there, that is set right next to this, and then we jump, there's a swing arm, a removable terminal block rather, that wires into the analog, and then you just open up the lid on that analog module and plug it in, and you're connected. And then, of course, the Micrologix 1400 with a straight-up digital field device simulator. You can build these. I mean, you can look at these and see everything you need to build one. Just buy the parts and build it. Well, we do one Micro 800. This is the Micro 810. I don't recommend the 810. It's a different beast than all the other 800s. But if somebody is hard-pressed to learn Micro 800, this is an easy way to go. You got 6 in and 4 outs. And 2 of the inputs are interconnected in those lit push buttons. You see our standard of a 24-volt DC power adapter, so there's nothing to get shocked off of. And then, of course, we include the USB adapter. You have to have that USB adapter. Believe me, don't buy a Micro 800 or an 810 because all that it has is the serial port, and the only way you can connect to it is through this little adapter. If you're going to do variable frequency drives, this is a good way to go about it. We have 2 items here, but you don't use both of them necessarily in class. On the left, you see a push button station with a potentiometer, selector switch, e-stop, and all that. On the drive, we have extended every single contact on that drive, and this is a PowerFlex 525 Ethernet. We've extended every single screw terminal out of the drive so they don't have to open the cover and booger up the screws and terminals on the drive. They can wear out those color-coded terminals on that DIN-rail strip. We also have a 3-phase motor, 230 3-phase. This drive requires 115 volts, so it can plug in. So we do have a 115 volt connection, but we try to make it as finger safe as is possible. What you can do with these 2 is you can hook up the push button station with a pot on the left to the drive on the right, and you can operate it just like a standalone drive. Or you can connect up those color-coded terminals on the drive demo to PLC inputs and outputs and Ethernet and run it from Micrologix 1400 or Compact Logic. So this is another way to go in your industrial automation training. Okay, we've covered quite a bit here. They need to be able to read, write, and do some math. It would help if they have visual spatial reasoning, that they have a little bit of understanding of physics, electricity, mostly electricity. They've got to have computer skills, and you're going to have to make sure that they understand industrial relay control circuits and symbols, because there's not a whole lot of difference between what you see right there and what a PLC program looks like. And there's a reason that it looks that way. Now we need lab projects that reinforce the lectures. So you start out by lecturing on something. Then you put them into lab and you tell them what they're going to do. They do the hands-on stuff. Okay? This is where the rubber meets the road, the lab projects. If they don't reinforce the lectures, and if they aren't easy to follow and expose the unapparent nature of PLC programming as opposed to just the apparent, in other words, the obvious stuff, then they're not going to have a strong grasp on PLC programming. Now, here's what we use for lab projects, and you don't have to buy these, you can come up with your own, but I'm going to show you what's in them. This is the oldest manual, and this was made with a Micrologix 1000. You could use this manual with any RSLogix 500 controller, whether it's Slick 500 or Micrologic. Very few differences. This one goes through quite a few instructions, some of which you'll never use. However, in the manual, we also have reading. It's not just lab projects. So here and there we have some, if you want to call it, discussions, discussing relays and relay logic. And we even do a little philosophy. Does automation eliminate jobs? And what is factory automation? And it goes through and explains how it got from A to B. We cover what we can with computer communication ports, RS-232 being the oldest and the most misunderstood. And then we talk about continuity. Now this is electrical continuity, but from here we go into logical continuity. You have to teach them how to use the software. RSLogix 500 Starter or MicroStarter and MicroStarter Lite. MicroStarter Lite, that software along with RS Links Lite actually comes with this manual. But RSLogix 500, or rather I should say MicroStarter Lite, which is free, will only work with a Micrologix 1000 or 1100 controller. I don't advise that you go that route just to get free software, because the 1000 and the 1100 aren't even close to the 1400. So you're only going to spend a few more dollars to buy the license for MicroStarter and to buy MicroLogic's 1400s instead of 1000s or 1100. So they need to know how to use the software, get in there. I mean, what's the project view, ladder view, etc. Then here, these are some of the nice to know things on what the screen looks like. So in the manual, we do explain how you can set up your screen to display the way you want. And then we do applications. So we go through and we cover all the basic instructions, but then we do applications that make sense. And as I said, we use some instructions you may never use, like this one, fill file, where you want to fill a whole file with a value or a set of values. But we show you how to do it. I mean, you actually go through and you use these instructions to exercise your memory values to get the desired result. This is our standard practical application that we use in all of our manuals. It's a machine, if you want to call it that has a couple conveyors, it has some cylinders, proc sensors, photo eyes, barcode scanner, and then cylinders, like I said, that either stop products or push products. We have a drill motor with a bit that drills a hole in the part, etc. So we use this same virtual application in all of our manuals. That way, once you've learned it in one manual, you're not relearning the process. Instead, you're applying new tools to a process that you already understand. This is a case of exercising high-speed counter instructions using toggle switches instead of an encoder or some other high-speed device coming in. And then, of course, at the end of the manual, there's a lab on the message instruction with Ethernet. Now, the 1000 does not have Ethernet, but the 1100 does. So this is a lab that you may or may not be able to do. You're going to have Ethernet controllers, and you're going to have some switches and at least two people. Otherwise, you'll be talking to yourself instead of communicating back and forth with someone else. A better choice would be this manual, and it also could be used with the 1000, 1100, 1200, 1500, but this one was specifically written using the MicroLogic's 1400. But what's in it is there's not a lot of things in this manual that you can't do with a 1000, 1100, except for the Ethernet. And again, we have some discussions on what relays are, where they came from, and relating them to logical control. And we go into a little bit more depth with logical continuity. Now, this is showing the relationship between the field wiring interface, the logic panel wiring, and the field wiring to the output. Understanding your controller's RAM. And we go into more communication details than we did in the previous manual. And in both manuals, we discuss how to navigate and edit the data files, step by step. We don't leave out anything. Accept tests and edits. This is working with online programming, step by step. Once you've done this several times, then you don't need the step-by-step callouts that we use here. Now here's a practical example in this particular manual with conveyors and photo eyes. Here's another practical example using the digital field device simulator to simulate a conveyor system that has a grease reservoir or lubricating system that pulses lubrication out to the bearings for a certain length of time every certain interval. Here I'm showing 12 hours. Every 12 hours is going to put out a push of grease into all the fittings. This is that standard machine I showed you in the other manual. And here we're looking at, again, one of the fine details that's nice to know, and that's to do with search and replace. So search, find, and replace. Something very important if you're moving I/O around in an existing program, etc. Okay, so that's lab projects that reinforce the lectures. Now we need lectures and discussions about the lab projects. So typically, if you're in a university or a college, you have lectures on the subject. Then they put you in lab at a learning station, and you do projects that reinforce the lectures. When the lecture's done, you have a wrap-up session. That's a lab project lecture discussions. We can't put that in a book. So instead, we put it on a set of discs. If you happen to decide to use any of our manuals, well, you just get a set of the discs and you listen to them, and then you come up with your own discussions and wrap up. And feel free to emulate what we're doing. We have lab projects that reinforce the lecture in a live classroom. Besides lectures, and then lab. Then you have lab, wrap up, and discussion. And of course, if you're not doing this in person, then you have to put it on a video disc series, which is what we do. Now, this presentation is to share with everyone out there how to do a PLC class. How I do the PLC class. And I'm talking about both virtual or online and in a live classroom. So I've recorded these project discussions and lectures because remember that when you do a discussion on a lab project, you're not just discussing or giving what they should have gotten for results, but you're explaining the results. That's a very important part. Okay, so that's RS Logics, both 500 and 5000, which includes Slick 500s, all the micrologics, and the bulk of the installed base out there in the United States is Allen Bradley, period. The other brands, if you're talking to them, they'll play that down, and they have good PLCs, they have good products. But when you're training people that are going to have to support the installed base, you need to train them on that installed base. And of course, RS Logics 500, 5000 is very similar. Actually, when you're in a program for a Slick 500 or a PLC 5 or even a Micrologics, it's going to pretty much look all the same, including when you get into 5000. Now, 5000 presents some additional challenges. It's quite a beast. And the major element of 5000 that's the real beast is the tag database. With 5 and 500, including the Micrologics, the tags were all predefined arrays. They typically gave you one element of a predefined array, and then you could expand. You could create additional arrays of the exact same data type and structure. Whereas with 5000, it's a whole new ballgame. It actually gives you the best of everything. There's another product that fits in the PLC arena, and that's the Micro 800. I can't address the installed base out there, but I know that there are a lot of schools using the Micro 800 for training because they're so inexpensive. What the installed base is, I don't know. If you're going to do Micro 800, this is the set of manuals that we use. We broke it up into two bindings because it got to be too cumbersome in one spiral binding. We just call it part 1 and part 2. It's just one manual, but it's in two bindings to make it easier to handle. Let's look at part 1, the first binding. And the Micro 800 is a completely different animal than Micrologics. So everything is different about Micro 800 and actually more difficult, but still very doable. And the software is free unless, of course, you want the developer's edition, and that's $100, $200 more. I can't remember the exact cost. In the manual, we do go through all of the procedures to set up everything, picking your controller, setting up the I/O, and then we start doing logic, and we start out with all the basic instructions: truth on, truth off, energize output, latch, unlatch. Now, they have a slightly different name for their instructions, but they look the same as they do in 500, and 5000. It still looks like ladder logic diagrams. And we have discussions. So this is not a lab project. This is actually a discussion where we are relating the relationship between the devices in the field wiring, the memory locations, the logic that reads those memory locations, and writes to memory locations that then affect the state of the field wiring. And of course, we have practical examples. You recognize this one. If you did some of the other manuals, it's a lubrication operation to send out a pulse of grease to all the zert fittings or bearings on a conveyor system. In part 2, we continue on, and here is a conveyor application, comparison instructions. Again, comparison instructions greater than, less than, and of course, if you've done other PLC Professor manuals, you recognize our standard virtual machine that we use to write sequencing programs. Barcodes, scanners, cylinders, and step-by-step through this manual. In-depth explanations, the lab results, meaning that we tell you what code to write, and then we show you how we wrote it just in case you didn't get yours to work. But we always tell you to, by all means, go off and do it your own way, and if it doesn't work, then copy what we did. Output devices. Now, in this little section, we're actually explaining to you how to build your own demo. So I'm showing you how to connect up a bulkhead power jack from a power adapter through an on and off switch with a pilot light to that particular controller. Now for 5000, RS Logix 5000, now we're stepping up the game here. Again, this was one large manual. We broke it up into two pieces, into two bindings, but it comes as one manual on the website. What's different about these two and the way they're divided up, and by the way, you notice it says RS Logix 5000, Studio 5000. They're one and the same thing when it comes to the license, not when it comes to the installations on your hard drive. Once you get past the front end or startup on a project, you're not going to be able to tell the difference between Studio 5000 and RS Logix 5000. What we did was we took all the practical examples out of the manual and put them into programming examples. In the fundamental programming manual, at key points, it will tell you to go to the programming examples and do a particular lab. We did this specifically to comply with requests from schools, college professors, university professors that want all the fundamental stuff in one spot, and then they can decide what lab projects they want to assign. In some cases, they have their own lab projects that they have the students do in addition to our lab projects. So it's broken up into two parts, fundamental programming and programming examples. In the fundamental programming, we talk about hardware, we talk about RS Logix 5000 Enterprise level, revision level 20 and lower, and then we're revision 21 and higher, which is Studio 5000. So we go through and explain all these differences. We talk about different processors, their I/O structure, talk about how to use RS Links and RS Who, and how to change the firmware level when you're adding an I/O module. We explain the relationship between memory locations and screw terminals on an I/O module. We talk about output and input or I/O buffering. Not going to explain it, it's in the manual. We talk about the different processing structures for different compact and control Logix controllers, because there's quite a few of them. Here's an example of the relationship between the field wiring, the memory location, inputs and outputs. And of course, we go through all the standard instructions, true if on, true if off, energize output, latch, unlatch, timers. And here's a mask instruction. We explain masks. Now we're getting into, this is the only practical example or illustration in this half of the manual. All of the others are in the other half. User-defined data types. Then in the programming examples, we'll say 90% applications. So here we have a 3-conveyor application. We show you the code. Here's that grease fitting or the lubrication system. And the reason that we use the same practical applications in all of our manuals is because if you follow the proper or the most effective path, you're going to learn 500 first, then 5000, because it's easier to learn with MicroStarter and a 1400. And then you get into 5000, and now all the ladder logic's under your belt. Now you've got to deal with the data table and the tag database. So if we reuse the same applications, then the student isn't forced to deal with two new things at once. They recognize the application. Now they can apply RS Logix or Studio 5000 to that same application. Conveyor application, indexing conveyors or indexing cartons onto a conveyor, buffering, and then an elaboration on that same lab. And in this case, we're using proc switches to identify a set of pegs on each pallet to identify the pallet number. But the reason we're doing this is to use the mask move instruction. Here's our standard virtual machine again. And in this case, because we built our digital field device simulator to support the projects and not the other way around, we can identify which switches go with what functions on that virtual machine. And of course, we do all the logic. Now this is a particular style of sequencing called latch and unlatch. It's the easiest to program, but it's very cumbersome. This is not the method that we recommend, but what we do in the manual is we allow the student to program it this way. Then we show them how to edit it to a different style and edit it again to yet a third or a fourth style of programming. So here you can see you don't see any latches or unlatches. It's all energized output. We also do communication labs. And of course, to do that, you have to have more than one processor. Otherwise, the processor has no one to talk to. And we do a lot of elaboration on different types of I/O and how to find the states of the I/O in your I/O tag database. And we also cover many more advanced functions like flashing the firmware. For the more advanced projects, we have yet another manual. This one is still in one binding, but it's not quite as large as the other one if you put both those black and blue ones together. In this one, it's more advanced subjects. Now, this particular subject really allows you to make an easy transition from RS Logix 500 to 5000. We do a very detailed comparison between what the project looked like in 500 versus 5000, or PLC 500 versus 5000. And we talk about events and tasks, how to set them up. And here we're talking about how the controller communicates over the backplane to different types of module. And it also explains the isolated nature of all of these program files and processor files, because the processor has global tags and then each program has its own local tags, and you cannot access another program's tags from a program. All the programs can access the global tag, but a program can only access the global tags and its tag database. Here we're showing multiple program files. Tasks, programs, routines, add-on instructions, conveyor, application, predefined data types, we explain those, add-on instructions, math, which we consider an advanced subject, function block diagrams, structured text, sequential function charts, in motion, the initialization routine. You notice disable rotary axis, push button, enable, etc. So this is the initialization routine for motion. Motion axis move instruction, and then we go into a little bit more depth on add-on instructions. And here's an example of an add-on instruction where we've embedded a lot of code, and this is a single instruction that does diagnostics on a cylinder. In this case, it's a tandem cylinder. Real quick here, if you want to see more detailed information on any of these stations or manuals, you go to products. It's broken up into 4 categories, and that's the Micro Starter Lite with MicroLogix 1000, 1100, and then 500 with MicroStarter, which is the software you buy, with the 1400, and then 5000 beginner, and then more advanced for 5000. Then there's also, to come yet, a section on the Micro 800. But of interest is, in the virtual classrooms, I mentioned earlier programmable logic controllers, room 102, an introduction, and then here's where you can listen to some of our classroom lectures. You can also go back to virtual classrooms, and here are the lab project discussions. It used to be broken up into basics, advanced 1 and advanced 2. Some of these are really old, the recording software is not good, and it's grainy, but it's free. And here are all of the MicroLogix 1400 lab project discussions. Right now they're available free through the website, but I can't guarantee that that will continue for any of this. And we do have Micro 800 lab project discussions, but they're not complete yet. But there's enough here to wet your whistle or to get you started. See, we go up to part 11 into timers, and we didn't get any further yet. So please avail yourself of all of this information, and the result of all this should be a happy learner that walks out onto the shop floor with a laptop and tools. Our whole aim is to assist you in developing people to support manufacturing that uses PLCs.